Hi, everyone. Welcome to my talk, None, Null, Nil, Lessons from Caching and Representing Nothing with Something. My name is Felice Ho. I'm a native New Yorker. And if you're visiting from out of town, welcome to New York City, and thank you for coming. I'm currently a data engineer at Equinox Fitness, where I build data platform tools, backend services, and work on open source projects. I'm also an organizer for New York City PyLadies. Here's an overview of my talk. First, I'll explain the scenario. I'll talk about the what, why, where, and how of caching. Then I'll discuss the problem with nothing. And then we'll go into a segment called We Have a Problem. I'll explain the root cause analysis, followed by lessons, and concluding with the value of nothing. So this talk is inspired by a fun saying I stumbled upon. I'm talking about caching and cache invalidation because, as Karlton once said, there are only two hard things in computer science: cache invalidation and naming things. And if you're wondering how this quote was first discovered, look no further. Here it is. According to Martin Fowler, the first place anyone found it on the internet was in Tim Bray's blog. And Tim said that he first heard it around 1996 to 7. So my goal today is to share some lessons with you on what I've learned from caching, and for a scenario and solution we've had in production for the past few years. First, how do we invalidate data in a cache? And second, how can production break down from nothing? And to do this, I will first explain caching in our scenario. A cache is used to improve user experience. It is temporary storage of data so that that data can be served faster at a later time. So there are many different kinds of caching, but I'll be talking about the kind that's very common on the web, server-side caching. You may want to do this if you have an application that becomes more resource-intensive as more requests are being made. For example, if you had to fetch data from a database. So when you have a high volume of requests, it becomes a burden on the server, causing a bottleneck, slowing down the performance of your application. So server-side caching helps with reducing server load, improving app performance. Separately, you may want to cache data if you expect to read that data more than one time. Then there becomes a benefit to caching that data somewhere so that you don't incur the expense of fetching that data more than once. So data caching helps with fetching data once, read more than once. Now, a fun way I found to compare caching to is buying milk at the supermarket. So let's imagine that we have a farm and cows somewhere responding to our requests for milk. Now, there's a high demand for milk, and the farm wants to sell milk to as many people as possible. But there's not enough refrigeration, so the milk spoils. Now, the farm may be distant from the end consumer, let's say city folks. So we can't simply scale up by adding more cows. There's limited distribution, and it's not scalable. So our problem is that there's a high demand or a large number of requests, but there's a limited supply of milk. And this is due to a slow response because of the limited computing power of our servers. Do you know what would help with the demand? If we had supermarkets to store the milk. For high demand, milk is always available at the market, so it's reliable and quick to access. For expiration, there's much more refrigeration in the markets, so they can store the milk longer and therefore determine when the milk expires. There's an update strategy. For scalability, by distributing milk to markets, it becomes more accessible to the end consumers. So with this solution, markets and not cows handle the demand of consumers. Cache invalidation. So I won't go into detail about why this can be a hard problem, but in the simplest sense, data changes without you knowing about it. So whether there is a change in data, no data, or new data, we want to make sure that the cache gets updated. Cache invalidation is also important because data in a cache is temporary. When does this data expire? How do we determine that data is not valid? Data changes, and the cache needs to get updated or data removed. So going back to our analogy, the market needs to know when the milk is expired or not valid and remove it from the shelves or delete it from the cache. So why are we caching, and how can it help you with app performance? So about 2 years ago, we were in the middle of simplifying our backend infrastructure, and I was asked to help build a cache. Due to a slow website and app performance. One of the reasons being, we have multiple data coming from different sources. So that meant that a single request to load a page could mean multiple requests to fetch data from different places. Another problem was that we had multiple applications accessing the same data content in different ways. So multiple applications were running the same queries at different times, and this was creating a high burden and load on databases. So the ask was, instead of overwhelming systems with tons of requests, why don't we store commonly used static data in a cache to provide applications with quick retrieval of data? Let's make it easier to build high-performing web applications with fewer errors and quicker response times. Not only does caching help with app performance, it also helps with database performance by relieving SQL load on databases. It provides an easier and more reliable path to data, and it provides consolidated data, so a source of truth and consistent data across all of our applications. Where are we caching data, and how can it be accessed? We are using Redis. Redis is an open source in-memory data structure store. It has built-in replication, it's highly available, fault-tolerant, and highly scalable. And for cache access, we are providing this through a backend service. The consumer has access to fetch data directly from the cache, or built into the API is a cache miss functionality where if the consumer is trying to fetch data from the cache and it's not there, the API will go directly to the database, fetch the data, save it to the cache, and return the same data back to the consumer. How are we caching data? So before we determine how we are caching data, we have some factors to consider. The first being an API contract. An API contract is an agreement between a service and a client. It provides specifications on the data and structure to be expected. And this is especially important in a mini-services architecture because it provides the server with the freedom to implement however it likes, while the client can be implementation agnostic. So what we are concerned about is that we need a JSON response string. Another factor to consider is the API design. Should we have a dynamic or a strict structure? And what I mean by this is whether or not we should include null values. If we have a strict structure and we include null values, this helps to indicate the existence of a property even if there is no value. But we would need to handle non-nullable values, non-nullable fields. If we have a dynamic structure where we do not include null values, this helps to remove noise, and omission generally represents a lack of value, but it is unclear if omissions mean unknown or truly no value. So here, we're not sure if I've had no talks or it's unknown whether I've had prior talks. Having a dynamic or strict structure also depends on your data. Do you have sparse or do you have dense data? Would you like your API to return one value set and 99 values null? Well, in our case, we decided that we do not want null values included in the API response. Another factor to consider, the data itself. So as I mentioned before, we have data coming from multiple places. We have transactional point of sale, web and application data coming from SQL Server. We have CRM data coming from Salesforce. And we have data warehouse data coming from Redshift. So we need an update strategy that includes all of our data sources. So for our update strategy, we do something called cache warming by having daily batch cache updates. And this is to ensure that important data is already always in the cache. Something else we do is all of the data that lives in the cache has a time to live. And this is where we proactively assign an expiration to avoid unexpected LRU, or least recently used eviction of data. As I mentioned before, we also have a cache miss functionality in the API. So we need to ensure that there's accurate and relevant data in the cache. So now we can get into some caching options in Redis. The Python interface to Redis can be installed using pip install Redis. And once you have the server running locally on your machine, this is how you connect to it. The first option is the most basic, to cache as a JSON encoded string. So here we have a dictionary to store our key value pairs. And then we are dumping that dictionary into a JSON encoder. And then we're performing an hset method in Redis to store that data in Redis. And this is what it looks like on the right side. So it's, we have a category, and then we have a JSON string cached to that key. The second value is to use something called rejson. And this is a module in Redis that allows you to store native JSON data types. And to use this, you would need a different library. It's called rejson. And so here, again, we have a dictionary. But instead of JSON encoding it, you can build your JSON object and then perform a JSON set to store that full JSON object in Redis. And then the third option I'll talk about today is caching as hashes. Hashes is Redis's native way to store key value pairs. So once again, we have our dictionary. And then what we do instead here is perform something called a hash map set to directly cache the keys and the values in Redis. So what's great about this option is that you can keep adding more keys and values to a hash without having to build the full object first. So for caching strategy, we have tried both JSON strings and hashes in production, and we actually noticed no notable performance difference. We actually saw that hashes were slightly faster with the help of using Lua scripting and the CJSON module to build the final JSON object. So now that we've discussed caching, our scenario, the caching strategy, let's talk more about cache invalidation. Specifically, the problem with nothing. Representing nothing with something. Why is this important? Because we should keep a placeholder value for keys even if they are null. We should recognize that data has changed from existing to not existing, else it appears as if something exists when it doesn't, causing invalid data in a cache. What is null? So I'm talking about null in the context that it is a value assigned to a variable to represent any of the following: no value, neutral behavior, an absence of data, non-value, an absence of useful value, or just nothing. It is represented with zeros, but it's not the same value as 0. So if you look at the ASCII map, null and 0 were stored with different values. So what is the problem here? The problem is that the serialization of null is represented differently. In Python, it's none. In JSON, it's null. In Lua, it's nil. And in Redis, it has no concept of null values. It's just not possible. It is up to the language or library to determine how to represent null. So here are some options for storing null in Redis. The first is storing as an empty string. But then, is the value actually an empty string, or is it null? Yeah. So here's a fun image I found to try to to interpret what's the difference between an empty string and 0 and null or undefined. Here's the second option. You can use the sentinel value to represent null. But a string null is not the same value as null. So be careful what sentinel value you choose. It would be bad if your sentinel value was in someone's name. You wouldn't want a scenario like little Bobby Tables here. So how do we handle the problem with nothing? By trusting your encoder to serialize into what you need. Keep your null values in native format before you encode it. So if you're mapping key value pairs from a Python dictionary to a JSON string, keep your null value as none before you send it into the JSON encoder, and trust that the encoder will return a null for you. And if you're mapping a key value pair from Redis using Lua to encode to a JSON string, you should translate your Redis sentinel value into null so that Lua knows that you want to represent that as null. So I've been using encoding and serialization interchangeably, but technically there's a difference. An encoder helps with converting data into a certain representation from one format into another. So, for example, from Python to JSON. Serialization is the process of translating an object into a format that can be stored or transmitted and reconstructed later. So JSON is a serialization format used for client-server communication in web applications. So at this point, I have explained what caching is. I talked about cache invalidation, our scenario for caching, the caching strategy, and the problem with nothing. So one morning, after a major release, a manager of one of our consumer apps comes up to me and tells me, we have a problem. The problem was this: could not convert string to date time null. This was a problem because our consumer is using a statically typed language. The consumer is also directly fetching data from the cache. Now, if you remember, Redis does not have a way to store null values. So Redis was returning a string or text value containing null. The consumer was trying to construct a date time from the string null, but datetime only accepts datetime or an actual null. So this was causing errors in production. String null is not the same thing as null. Now, when it comes to discussing the root cause analysis, imagine a conversation that goes something like this. Well then, why did production go down today? Nothing took down production. How can nothing take down production? From introducing nothing. What do you mean nothing? What new thing did you add to the cache? We introduced nothing into the cache. Then why did it go down? Previously, we provided only something, but now there's nothing. There's also nothing. So what caused the problem? Nothing. So here are some lessons and takeaways. First, represent nothing with something, but some gotchas are: nothing is recognized differently. Handle non-nullable values appropriately. And be aware of how your source data systems and tools handle null values. Another lesson is to left join important data. Include records with values at one point that matter if they no longer have values, or otherwise not removed through the time to live. And lastly, trust your encoder. Serialize nothing in native form, no matter which language, tool, or format you are using. And so, what is the value of nothing? Well, one might say that it's worth $1 billion. In fact, the inventor of the null reference called it a $1 billion mistake. In 2009, Tony Haw said, "I call it my $1 billion mistake. It was the invention of the null reference in 1965. I couldn't resist the temptation to put in a null reference simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. But in seriousness, I have learned to embrace the value of nothing. Even though the value of nothing broke down production, there is a value to nothing of representing nothing with something, because it helps with overall caching, specifically cache invalidation. And it ultimately helps with the big picture of app performance. It has helped our web applications with reduced errors and quicker response times, while reducing SQL load for our databases. And so today, I hope that I've inspired you to think about the value of nothing. Thank you.